In this video, we are looking at quadratic equations. We will look at several different ways to solve quadratic equations, including factoring, completing the square, using square roots, using the quadratic formula. We'll also look at quadratic polynomials as functions, and we'll look at the important features of their graphs. Now, when we talk about quadratic equations, we're talking about any equation that can be put into this standard form. When we do all the simplify and combine like terms and put all of our terms on one side of the equation, it will match this form: ax squared plus bx plus c equals 0. A cannot equal 0. A must be some non-zero number, but b could be 0 or c could be 0. Here's our first example: 3x squared minus 6 equals 7x. The first thing we should do is put this equation into standard form. Let's collect all the terms on the left side. So the positive 7x will move over to the left side. It becomes negative 7x. And we'll put these in a descending order to get 3x squared minus 7x minus 6 equals 0. Now, when we have our quadratic in this standard form, there is a related quadratic function. We could say that f of x equals 3x squared minus 7x minus 6. And what's important for us to realize is that the relationship between this quadratic equation and the quadratic function, we really can only see it when our quadratic equation is in standard form, meaning we have all of our terms on one side of the equation equal to 0. Only then should we look at the comparison between the equation and the quadratic function. Now, what if we wanted to solve this quadratic equation? We do have several methods. The first one I'll use with this example will be by factoring. Now, this trinomial 3x squared minus 7x minus 6, it has a leading coefficient of 3. So in order to factor, I'll use the AC method, where my first move is to multiply my first and third coefficients. That positive 3 times negative 6 equals negative 18. And now I'm looking for a pair of numbers that multiplied together would equal this negative 18, but added together would equal negative 7x. So I like negative 9 and positive 2 for those numbers, and we're splitting up this negative 7x into two terms using those numbers, negative 9 and positive 2. And a quick reminder that the order won't matter. So if you place the plus 2x first and then the minus 9x, it will work out to be the same factored answer. But basically, what we've done so far is broken this trinomial up into four terms that is in great shape for factored by grouping. So from the first two terms, we're looking for what's the GCF. So we can divide out a 3 and an x from each of these first two terms. That will leave us with x minus 3 in parentheses. From this second pair, we're also looking for a GCF. 2 we can divide from each of these terms, and that will leave us with x minus 3. And when factored by grouping, it's critical that this quantity in the parentheses matches up. So both sides are x minus 3. It means we can proceed to our final factored answer, where we use the x minus 3 once, and then these GCFs, the 3x and the positive 2, become terms in our other factor. So now we have a factored polynomial. 3x squared minus 7x minus 6 is factored into x minus 3 times 3x plus 2. And just how we factor this polynomial, we could factor this quadratic function. So another way to state this quadratic function is in factored form. F of x equals x minus 3 times 3x plus 2. Now back over to this side, remember we were factoring so that we could come up with the solutions to this equation. So the last step is that each of these factors, we're saying these two factors multiplied together equals 0. Therefore, one or both has to also equal 0. It's the only way we can multiply two things and get an answer of 0. So if the x minus 3 equals 0, that gives us a solution of x equals 3. If 3x plus 2 equals 0, now don't be too hasty here. Remember, we're doing our moves to solve this linear equation. So I'd subtract 2 and then divide by 3 to get the other solution, x equals negative 2/3. So on the left side, we have an example of taking a quadratic equation, solving it by factoring, and this should be a set of moves that we've done before. But what does it mean in the context of functions? We can see that a quadratic in standard form can be thought of as a quadratic function. The function can be written in factored form. And lastly, when we're talking about solutions, in the context of functions, we call them zeros. So the zeros of this function are 3 and negative 2/3. The reason we call them zeros is because they are solutions to setting the function equal to 0. So we can see all these pieces fit in with one another. Here's where we called our quadratic function f of x equals 3x squared minus 7x minus 6. When we decide that we're going to solve the equation f of x equals 0, we can see, well, if we're deciding that f of x equals 0, it means that this f of x equals 0, and then we would have an equation that is identical to this quadratic equation. One last aspect we really should know is when we're talking about solving the equation f of x equals 0, understand that f of x works the same way as y. So we're talking about a situation where y equals 0. And if you think back to graphing, one thing that we know is that when our y-coordinate is 0, we're talking about the x-intercepts. And when the x-coordinate is 0, we found y-intercepts. So when we find zeros of a function, not only do we have these solutions to the related equation, but we also have found the x-intercepts on the graph. Okay, that's key for us to understand. The zeros of the function are going to be x-intercepts on the graph. And the reason is because we have set our y value equal to 0, and if your y value equals 0, that automatically means you're talking about x-intercepts. You're talking about coordinates where the y value is 0. So let's take a look at this graph. Here are those x-intercepts that we found, the points where the y-coordinate is 0, and they occur exactly at those zeros that we found algebraically, positive 3 and negative 2/3. Just to talk a little bit more about the graph, do we know about this point down here? So this is the vertex of the parabola, and all of these quadratic functions will have this basic shape. It's called a parabola, and the points of interest are definitely going to be our x-intercepts, and also this point, the vertex. So let's just make sure we're smooth with some information about the vertex as well. The way to find the vertex of the parabola is to use the formula. The x-coordinate of the vertex is at the point negative b over 2a. And remember, a, b, and c are our coefficients of this quadratic function. So a equals 3, b equals negative 7. Let's plug those into this expression, negative b over 2a, and it equals a positive 7 over 6. So we know that the x-coordinate of the vertex is 7/6. How would we find the y-coordinate of that vertex? Well, what we have to do is take this x-coordinate and evaluate the function at that point. So we're going back to our function and putting a 7/6 in place of each x. And let's do the simplify. So let's take care of this exponent first, just squaring numerator and denominator. Multiplying these coefficients, we'll get a little bit of simplifying of the denominator here. It leaves us with this expression. We have maybe a shortcut here because we could see that 49 over 6 is twice as large as 49 over 12, but we'll just go ahead and get common denominators for these other two fractions. 49 over 6, we'll do top and bottom times 2. This 6, which is 6 over 1, becomes 72 over 12, and now we have a common denominator 12. Let's subtract across these numerators to equal negative 121 over 12. As a mixed number, negative 10 and 1/12. So that should be the location of that vertex that we saw on the graph. Our x-coordinate is 7/6, the y-coordinate negative 10 and 1/12. So positive 1 and 1/6 for the x value, and then down to negative 10 and 1/12. So there is our vertex, and it's one final good lesson about we really cannot rely entirely on the graph. In the future, we will definitely use aspects of the graph to help us solve problems algebraically, but we really cannot make any assumptions. With the vertex, it almost looks like our y-coordinate would be negative 10 but we just showed that it's actually a little bit further than negative 10. It's negative 10 and 1/12. So just a good lesson that we can use the graph at times, but in order to really verify our numbers, we should do that part algebraically. Here's our next example, x squared plus 5 equals 25. We could take a similar approach as to what we did in the previous problem, but we're going to go in a different direction this time because this equation has an x squared, but it has no x term. We could say that the value of b equals 0. b is the coefficient of x in that standard form, and if we don't have a term with just x to the first power, it means that the b coefficient was 0. Problems like these we could solve by isolating the x squared and then doing a square root of both sides. Let's do this. So let's move the positive 5 over to the right side. It becomes negative 5, so we're left with x squared equals 20. At this point, we do square root both sides because square root of x squared will leave us with just x. But there are some very important things to understand when we solve an equation by using square roots. First thing would be that we get a result that could be positive or could be negative. That always must be included when we solve an equation by doing a square root on both sides. So I even have the habit of, as soon as I do my square root on both sides, I go to the next line and put my plus positive or negative, plus minus symbol right there so I don't forget. So what do we have on the left side and the right side? We said the square root of x squared equals x. And on the right side, a square root of 20. It's not rational. The 20 is not a perfect square, so we won't be able to take this radical down completely simplified, but the 20 does have some factors that are perfect squares, so we should simplify a bit. When we're simplifying radicals, basically our prime concern is our radicand, the number inside the radical, is it made up of factors that are perfect squares? Because any perfect squares, we should simplify those out of the radical. So I know 20 is made up of a 4 times 5, and I know square root of 4 is 2. So I will have a 2 outside of the radical, the 5 will stay inside the radical, and I've brought down this symbol to indicate that I could have a positive answer or could have a negative answer. So what would the related function be for this quadratic equation? Remember, we're looking to set it up in standard form with all of our terms collected on one side equal to 0. So once I have done that move, then I could say what the related quadratic function is. So taking the 25 and moving it over to the left side as a negative 25 will leave us with x squared minus 20. There's our quadratic function. What else do we know? We want to know about the zeros. So the zeros match up with the solutions. Our zeros are positive 2 radical 5 and negative 2 radical 5. Now the zeros, we know that they are also going to be our x-intercepts. So let's get some decimal approximations just so that we can confirm that we have these zeros, or at least we can show that we're approximately close on our graph, that 2 radical 5 and negative 2 radical 5, which are approximately 4.5 and negative 4.5. That's where we'll see our x-intercepts when we look at the graph. Now we also want to know what are the factors. We saw with the previous example that there was a very clear connection between the zeros and the factors. But in this case, we did not factor our quadratic. We solved it using square roots. So we haven't really uncovered those factors so far in this problem. And if you went and looked at x squared minus 20 to think about factoring, you'd encounter this binomial that in the past we would have said you cannot factor. If this was x squared minus 25, we would have a difference of squares that we could factor. But right now, we don't really have a difference of squares. We have to take basically the backdoor route. We just found the zeros, and we know there's a direct connection between zeros and factors. If 2 radical 5 is a 0, it means that a factor was x minus 2 radical 5. And for the other 0, negative 2 radical 5, that comes from a factor of x plus 2 radical 5. So we're basically thinking about that last step of solving a quadratic equation by factoring. In our previous example, once we had it factored, it was x minus 3 times 3x plus 2. And just think about that first factor, x minus 3. When we solved that, when we made it x minus 3 equals 0, it led us to the solution of x equals 3. So we could very clearly see this connection between a 0, once it's in a factor, it will have the opposite sign. And I could think about if I made an equation, x minus 2 radical 5 equals 0, and solved it, it would lead me to x equals 2 radical 5. So we can still set up factors even after we've found zeros, and we haven't yet found the factors in any other way yet. And lastly, we know that these are factors because if we were to multiply them together, it would equal our original function. So we're now even into a new area where we can talk about factors in problems where in the past we said it could not be factored. So we really want to embrace this idea that problems before that could not be factored, actually we do have ways to look at them in factored form. And often we get there by solving the equation first to get our zeros, and then we can make the factors out of the zeros. But we'll be checking in on this idea with the future examples. Before we move to our next example, let's take a look at this graph. We want to spot, do we have our x-intercepts here? And also, what do we know about the vertex? I think we should know two things. If we know about our transformations, we know that this function is our standard parabola y equals x squared, but then it's been shifted down 20 units. So its vertex ought to be right on the y-axis. If you think about using the formula for the x-coordinate, negative b over 2a, here, remember, our b value is 0, so that fraction negative b over 2a would equal 0. So a few different ways that we could really see that our vertex is going to lie right on the y-axis. But let's look at this graph. So here's our parabola shifted down 20 units. The vertex is right on the y-axis. And we see our x-intercepts are at approximately negative 4.5 and positive 4.5. Here's our next example. X squared plus 6x plus 9 equals 36. This would not be one that I would choose to solve using square roots right off because we have an x squared term, but we do also have a first degree x term. Some options for us would be that we move this 36 over to the left side and then try to factor that trinomial. But one thing that I want to spot here is that this trinomial as it is right now is a perfect square trinomial. What we're looking for in that case is if we multiply our first and third coefficients, it should give us a perfect square. In this case it does, it's 9. And our coefficient in the middle should be twice as big as the square root. So the square root of 9 is 3, and there we see the 6, a number twice as big as 3. So we've got a perfect square trinomial. It is x plus 3 squared. On the right side, that's even a perfect squared. That could be useful for us. So let's just bring down the equals 36. And in fact, now we are in a good spot to use square root both sides. The way we dealt with having an x squared and a first degree x, when we have it as a perfect square, we're able really to almost isolate that x on the left side. So a square root on both sides is going to work for us. I've got the plus minus symbol ready to go. On the left side, the square root and the square will cancel. We're left with x plus 3. On the right side, we have a rational. Square root of 36 is 6. Now, just be cautious here. It would be a mistake to just subtract 3 from both sides and try to subtract 3 from that 6 with the plus minus symbol still there. We really need to understand that this is an abbreviation for two different equations. We're saying x plus 3 equals positive 6, or x plus 3 equals negative 6. And now, once they are separated into two equations, now let's solve. Subtract the 3 from both sides will lead us to one solution of x equals 3, but another solution of x equals negative 9. So be cautious about how we finish up these solutions when we have to work in the plus minus symbol. So let's tie these things into our concepts about functions. What's the function? What's the related quadratic function? We know that we see that by collecting all of our terms on one side. So move the 36 over to the left, make it a minus 36. That's going to give us x squared plus 6x minus 27. There's our quadratic function. what else do we know so far? Well, we have our solutions, and we know those are the zeros. So we've got the zeros of the function, positive 3 and negative 9. Lastly, let's talk about the factors. And we have a couple choices. So with the last problem, we came up with our factors after finding the zeros. We would say if a 0 is positive 3, the related factor is x minus 3. And for the 0 of negative 9, the related factor would be x plus 9. So that's one way we could go to come up with those factors. Or we could look at this quadratic function and think about, could we factor this? We'd look for a pair of numbers that multiplied together equals negative 27, but added up equals positive 6. And we would come up with those same two results, x minus 3 and x plus 9. Lastly, we're going to look at the graph. We want to make sure that we spot some x-intercepts at positive 3 and negative 9. And of course we will. There they are, positive 3, negative 9. And we have a vertex this time. It's way down low. But if you think about using that expression negative b over 2a, that would give us a negative 6 over 2, a negative 3. So everything is still working out. Our vertex is at an x value of negative 3. And if we wanted to find the y-coordinate of that vertex, we would take that negative 3 and plug it in place of each x here. So that would give us a positive 9, minus 18, minus 27. That's a negative 36. So we are seeing our vertex at x equals negative 3, y equals negative 36, way down low. Now our next example, 2x squared plus 3x minus 4 equals 0. We're going to build off of our technique that we used in the previous example where we saw that we had a perfect square trinomial that led us to a pretty nice solution using square roots. Now, we can always come up with a perfect square trinomial, even if it's not laid out nicely for us at the beginning of the problem. Here's what is required, and we will have to complete the square. That's the name of the process where we create a perfect square trinomial. To complete the square, you need to know that we only complete the square when our first term, that leading term, is x squared. Basically, our coefficient must be 1. We don't complete the square if we have a coefficient that is anything else but 1. So in this problem, I will need to divide every term by 2. It's going to take this 2x squared down to x squared. The 3 divided by 2 won't divide evenly. I'll keep it a 3 halves. The other thing is, for completing the square, we like to have our first two terms, but I'd like to have a space here for the third term because we decide what third term, what constant term do we need to create a perfect square trinomial. And I like to have it blank for now. So this negative 4, and definitely we said we're dividing everything by 2, so it would be a negative 2. I'm going to move that number over to the right side. So I definitely have a gap right here where my third term in the perfect square trinomial will go. So those are the two things that I need to do to prepare myself for completing the square. I need to make sure that the coefficient on x squared is 1. If necessary, that's going to mean dividing every term by the coefficient that's already there. And I'll move the constant over to the right side and leave a space here. The next step to complete the square would be to focus on our b coefficient, the coefficient of regular x. We need to do two moves. We need to take this coefficient, we need to cut it in half, and then we need to square it. And once we do those two moves, that will be the perfect constant for a third term that will give us a perfect square trinomial. Well, 3 over 2 cut in half. I think the easiest way when I get to odd numbers or I get to fractions is I know that multiply by 1/2 is a way that I could cut it in half. So 3 over 2 times 1/2 would give me 3 over 4. And then square 3 over 4 would be 9 over 16. Now, this 9 over 16, we have to make sure that we keep our equation balanced, so it gets added to both sides of the equation. Now, this is a perfect square trinomial. It is because we did those moves of cut in half and square. The number that we got just from cutting it in half, actually, is the number that shows up in factored form. So 3 over 2 cut it in half gave us 3/4. That 3/4 goes in our squared quantity. but the number that we used for our constant was what we got after we cut it in half and square. So the 3 squared gave us the 9, the 4 squared gave us the 16. Let's put together these numbers that we have on the right side. I could just look at this like a mixed number, so I'll do 16 times 2 plus 9, keep the denominator of 16. So we're looking at 41 over 16 on the right side. Now it should look very similar to the previous example. We can do square root both sides. I'm ready here for a positive or negative answer. On the left, the square root and square will cancel to leave us with x plus 3/4. On the right side, the 16 in the denominator, I could simplify. Square root of 16 equals 4, but the 41 in the numerator could not be simplified, so that remains square root 41. Let's continue solving. Now, in the previous example was where we split this up into 2 separate equations, and it was because we were dealing with integers that we could combine. In this problem, I won't be able to combine this 3/4 with this fraction radical 41 over 4. We've got a rational number with an irrational number. So in this case, I can actually keep it on one line. I can continue to use this plus minus symbol. I'll just take this positive 3/4, move it over to the right side to make it a negative 3/4, and then I could have an expression here that shows my 2 solutions. One would be using a plus, one of them would be negative 3/4 plus radical 41 over 4, the other one would be negative 3/4 minus radical 41 over 4. And we usually see, it's not every time, but in my experiences, I most often see the irrational number coming last. So that was the reason that I put my negative 3/4 at the beginning. If you had an answer of positive or negative radical 41 over 4 with the minus 3/4 at the end, 100% correct. So let's talk about our function information. What is the related quadratic function? So it was set up actually right there for us. 2x squared plus 3x minus 4 equals 0. So we can see our quadratic function. Do we know what the zeros are? Yes, the solution down here, those are our 2 zeros. I'll write them out individually. Negative 3/4 plus radical 41 over 4 and negative 3/4 minus radical 41 over 4. But let's also talk about the factors. I'm working backwards like we've done before because this is a quadratic that cannot be factored. So I'm using the idea that a factor is basically x minus the 0. So in this first expression, I thought about using x minus this whole expression. And when I have 2 terms, I have to distribute that minus sign. So x minus all of this turned into plus 3/4 minus radical 41 over 4. And there's that first factor. This other one, I thought about taking this 0 and putting it into parentheses with x minus. So x minus negative 3/4. Again, we had to change that to a positive. And down here, minus negative radical 41 over 4. That had to become a positive as well. So if we're forced to write the factors of this quadratic function, my approach would be, let's solve it. Let's solve the related equation. Once I have the zeros, I know I can backtrack up into the factors where I think about x minus the 0, x minus this 0 as how I come up with these factors. Let's take a quick look at the graph just to make sure that we're spotting our intercepts at these 2 points. Ooh, it's tough for us to, I guess we could punch these into a calculator. This is radical 41, that is in between 6 and 7. So it looks like we've got a little more than 1.5. Take away 3/4. Getting a little sloppy there. You know, we don't want to estimate and eyeball too much, but it looks like we should get 1 0 at about 3/4, one at a little bit less than positive 1, and the other one's going to be, looks like between negative 2 and negative 3. So there we go. That first x-intercept is just before positive 1. And the other one is between negative 2 and negative 3. And of course, the exact values are those irrational numbers that we just found algebraically. So far, we've looked at solving quadratic equations by factoring, by using square roots, by completing the square, then using square roots, but we have not yet talked about quadratic formula. So let's do it with this example. X squared plus 8x minus 7 equals 1. If we are using the quadratic formula, the setup for that one is also get all of our terms into a standard form. So this positive 1, we need to move this over to the left side. As a negative 1, it would give us x squared plus 8x minus 8 equals 0. Let's lay out our quadratic formula. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. And of course we know that a, b, c are the coefficients. A is coefficient of x squared, so that's going to be 1. B is positive 8. C is negative 8. So we'll plug those values in. There's my negative b plus minus. I like to really go step by step inside the radical. It's just easy to go off path there. So b squared is going to be 64 minus 4 times 1 times negative 8. In the denominator, 2 times a is 2. So I have a little more work that I could do in the radical. This 4 times negative 8 is negative 32. So it's looking like 64 minus negative 32, or basically 64 plus 32, equals 96. Square root of 96. Now 96 is not a perfect square, but it does have some factors that are perfect squares, so it can be simplified. 96 is 16 times 6. So the square root of 16 becomes the 4 outside of the radical. The 6 remains inside the radical. And we have one final step. That would be to think about simplifying this fraction. And to simplify the fraction, we would need to divide evenly by all of the rational parts. So we ignore the 6 in the radical, but we have to be able to divide evenly from all 3 of these terms. And in this case, we can. We can divide each of these terms by 2. It will leave us with negative 4 plus or minus 2 radical 6. So we've come up with the solutions to this quadratic equation. Let's talk about the ideas about functions. So clearly up here is where we had our equation in standard form. That's going to lead us to our quadratic function of x squared plus 8x minus 8. Down here are solutions. Those are our zeros at negative 4 plus 2 radical 6 and negative 4 minus 2 radical 6. And I got ahead of myself a little bit here with the factors, but again, remember, to come up with the factors after we have the zeros, we are thinking about a set of parentheses where we have x minus a 0. So if I think about first using negative 4 plus 2 radical 6, plugging this number into parentheses with x minus would give me x minus negative 4, so that's x plus 4, and minus 2 radical 6. Here it's basically the same, but with our signs adjusted a little bit because we use negative 4 minus 2 radical 6. So x minus negative 4 became the positive 4. X minus negative 2 radical 6 becomes this positive 2 radical 6. And if you're interested and have a little bit of time, you can always take these factors and multiply them out just to verify that it would equal x squared plus 8x minus 8. So even in that sense, they truly are factors. Where multiplied together, they would equal our original expression. Let's take a look at the graph here just to make sure we see our x-intercepts at negative 4 plus 2 radical 6, negative 4 minus 2 radical 6. And there's our vertex. Looks like the x-coordinate is at negative 4. That makes sense if we think about the expression negative b over 2a. Negative 8 over 2 would equal negative 4. So all of our ideas so far are still working together. And I don't expect that we'll get to a point where they stop working together. We're going to see everything working together nicely. Now that we've looked at different methods of solving these quadratic equations, let's revisit 2 of our examples. Our very first example, and then also this most recent example. So the 3x squared minus 7x minus 6, and also x squared plus 8x minus 8. If you remember, one of these expressions could be factored, and it led us to some nice rational solutions. It led us to a positive 3 and a negative 2/3. And this, our last example, it did not lead us to rational answers. It was answers, zeros that had a radical part, and also if we thought about factoring, this was not an expression that could be factored using rational numbers. So we want to talk about how can we recognize those things are going on before we actually really dive in and do the work. What we should think about is focus on the quadratic formula. Why not? This expression b squared minus 4ac is in the radical. So if we use our values for a, b, and c and we plug them in, if b squared minus 4ac turns out to be some sort of perfect square, then it simplifies the radical and it leaves us with pure rational numbers, no radical left. But if we plug in b squared minus 4ac and we do not get a perfect square, it means that our answer is going to still have some radical part to it. It's going to be an irrational solution. So if we can just look at b squared minus 4ac and see what kind of number that is, that will be the clue as to what our final zeros might be, what types of numbers they would be. So in this example, b squared minus 4ac, the b is negative 7, so when we square that it would be a positive 49, minus 4 times 3 times negative 6. I'm still cautious about my signs when I do the 4ac. So this will become, let's see, 4 times 3 is 12, 12 times negative 6 is a negative 72, so 49 minus negative 72 is basically 49 plus 72. We add those up and we get 121, and that is a perfect square. That is 11 squared. So if I imagine that this was a square root of 121, which I could simplify to become 11, I'd have these two fractions, and this one's going to lead me to 18 over 6, my first zero of positive 3. And over here, I'd get a negative 4 over 6, my negative 2/3. So in this example, which we already knew we could factor, and we already knew the zeros would be rational numbers, we've just shown that if you just check out b squared minus 4ac, that will give us a clue as to whether our numbers will be rational or not. And if b squared minus 4ac is a perfect square, then we will have rational solutions. And the connection there is that if we have rational solutions, it means that this was a trinomial that could be factored. Those facts are all tied to each other. So let's talk about this one, which we found we could not factor, and it gave us irrational numbers for zeros. When we look at b squared minus 4ac, we should expect to see a number that is not a perfect square. And we actually just did this one. That was our 64 plus 32 equal 96. We saw that we could simplify because we had a perfect square factor of 96, but 96 itself is not a perfect square. So it left us with some radical part to our answer. It led us to two irrational zeros, and the connection there is that if we get irrational zeros, it means that we had a trinomial, or we had a quadratic that could not be factored. Okay? So perfect square in b squared minus 4ac means we will get nice fractions or integers, and it means that we were dealing with something that could have been factored. If b squared minus 4ac does not give us a perfect square, it means our zeros are going to be irrational numbers, and it means that we were working with a trinomial that could not have been factored. So what about if we talk about b squared minus 4ac being a negative number? And that's something that will arise if we use x squared plus 8x plus 20 as an example. So b squared minus 4ac would be 8 squared, that's 64, minus 4 times 1 times 20. Oh yeah, and let's mention this, that the b squared minus 4ac is a quantity that does have its own name called the discriminant. And based on what the value of the discriminant is how we know what the value or what types of numbers actually the solutions of the quadratic would be. Okay, so it's called the discriminant. That's the b squared minus 4ac. In this case, b squared minus 4ac is leading us to 64 minus 80, a negative 16. So what's happening now if you imagine that in that radical in the quadratic formula, we have a negative number? Well, we should know that negative in a radical is going to lead us to a not real number. Let's do more simplifying, because we can do that. This square root of negative 16, well, we know square root of 16 is 4, but because it was negative, we need to make this a 4i. So negative 8 plus or minus 4i over 2. And again, a situation where we can simplify, we can divide everything by 2. That will lead us to negative 4 plus or minus 2i. So our solutions are not real numbers, and our discriminant was negative. So we're adding another piece of information to our list about the discriminant. If the discriminant is a perfect square, we get nice rational zeros, and it means that we were dealing with a trinomial or a quadratic that could have been factored. If our discriminant gives us a number that is positive, but it's not a perfect square, it means we get those irrational zeros. We get answers with radicals in there. It also means that we were looking at a quadratic that could not have been factored. Now, if our discriminant turns out to be any sort of negative number, we get solutions that are not real, because the discriminant is always the quantity that is in the radical. If the discriminant is negative, we have to realize we're talking about doing square root of a negative. That's automatically going to be not real. Now, what is the graph going to look like? If we're used to talking about our zeros as x-intercepts, what should we expect to see on the graph of x squared plus 8x plus 20? So let's talk about the function information. X squared plus 8x plus 20, we could say that's our quadratic function. We have zeros here. Down here, our solutions are the zeros, negative 4 plus 2i, negative 4 minus 2i. If we wanted to come up with factors, we would put them in parentheses with x minus negative 4 plus 2i and x minus negative 4 minus 2i. So that minus is going to change this negative 4 into a plus. Our imaginary part will have opposite signs. One will have a negative 2i, one will have a positive 2i. And the last piece of information we were really focusing on when it came to looking at these quadratics as functions was that our zeros were also the x-intercepts. So if our zeros are now imaginary, where would we expect to see the x-intercepts, and how would this graph really look? We see the same quadratic shape, but we see that we actually have no x-intercepts at all. And this is going to be the outcome when we have zeros that are imaginary numbers. The zeros are our x-intercepts. If they are real numbers, we will definitely see those show up as x-intercepts. But if our zeros turn out to be imaginary, then we see our vertex is above the x-axis and that our parabola actually does not cross the x-axis anywhere. This is the outcome when we have zeros that are complex numbers. We have no x-intercepts. Let's talk just a little bit further about the discriminant. We've talked about the outcomes when the discriminant is a perfect square. We've talked about the outcomes when the discriminant is not a perfect square but still a positive number. We talked about when the discriminant is negative. It was that example we just knocked out where it led us to imaginary or led us to complex solutions. But we have not yet talked about what happens when b squared minus 4ac, the discriminant, equals 0. So let's go back to the quadratic formula and imagine what would happen if we had square root of 0. Well, square root of 0 is just 0. That entire piece is going to be cut out. Even the plus minus will also, because think about negative b plus 0 or negative b minus 0. Each of those would simplify just to negative b. So it left us with x equals negative b over 2a. And that's exactly the same expression that we used to find the x-coordinate of the vertex. So let's try to see if we can make that connection as well. But what we see so far is that it leaves us with just one answer. We don't have two separate answers that we get to from one using a plus, one using a minus. That part has been eliminated altogether by the radical being 0. So far, all of our examples have led us to two zeros, except now we're seeing that when b squared minus 4ac equals 0, that's only going to lead us to one solution. Let's take this one as an example, x squared plus 6x plus 9. This is a trinomial where b squared minus 4ac will equal 0. So the 6 squared minus 4 times 1 times 9. We're looking at 36 minus 36 is 0. Let's also look at what happens when we solve this the rest of the way using quadratic formula, and we go to negative b over 2a, negative 6 over 2 equals negative 3. So definitely we are seeing that our solution, we only get one of them, and that solution is right where the vertex is. We still know those zeros to be the x-intercepts on the graph, so we will see that we have only one x-intercept. It's going to be at negative 3, and that's also where the vertex of this graph will be. We can see it right there. There's our 0 at negative 3. We have the same parabolic shape. It does have the x-intercept, but it has only one, because since the discriminant was 0, we only get one answer in that case. But we do like to talk about these situations as the negative 3 being a double root. We do that for a few different reasons. Number one, we're going to establish a pattern where the biggest exponent we see in a polynomial function also indicates how many solutions or how many zeros we have. So anything that has x to the power of 2 really ought to lead us to 2 solutions. And all of our examples so far did, whether they were rational or irrational or complex, they all gave us 2 solutions, except for this one. So how else can we think about this being a double root, or some way that we could see this as really 2 solutions so that it's going to fit in with all of our other patterns? And what we can do is we can think about solving this one by factoring. If we factor, we see that we have x plus 3 as a factor twice, so that when we solve each one, we would get x equals negative 3, and we would get x equals negative 3 again. So from one perspective, we could say that we really still are getting 2 solutions. It just happens to be the same solution repeated. So all of our other ideas are still fitting in. We just want to understand that in this particular situation, when the discriminant equals 0, that's when it leads us really to only one solution, but we think about that one solution as a double root, or a double 0. And when we get to a double 0, we know that it does still show up as an x-intercept as long as it's a real number, but when it's a double root, it's not an x-intercept like our graph cuts right through it. It is that the vertex is right there, so our graph will just touch it. And here's that graph. Our vertex is right at negative 3, the x-intercept. It doesn't cross through, it just touches it and goes back up. It is right where the vertex is. So to wrap up, we have seen some graphs where the vertex was above the x-axis, no x-intercepts, and we know that means that we have complex zeros. We saw a graph where our vertex was touching the x-axis. That's where we had the single solution, or the double 0 solution. We see only the one x, but we know it can be thought of as a double root, because this is a case where our b squared minus 4ac equals 0, and in factored form we would see the same factor twice. And for graphs where the vertex is below the x-axis, we will clearly see our 2 x-intercepts, and we will know that we have zeros that are real numbers. They could be rational, they could be irrational, but they are both real.